Consider the following series. The first one, 1 minus 1 half plus 1 fourth minus 1 eighth plus 1 sixth, and so forth. This series, we can write it as the summation from k from 0 to infinity of negative 1 to the power of k times 1 half to the power of k. So when k is equal to 0, you have negative 1 to the power of 0, which is just 1, times 1 half to the power of 0, which is also 1. So you just get 1. So that's why you get 1 over here. All right. When k is when k is 1, then you have negative 1 to the power of 1, which is negative 1, times 1 half to the power of 1, which is just 1 half. So negative 1 times 1 half, you get negative 1 here, and so forth. Okay. Now look at this series. This is 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth, and so forth. So again, we can write it as negative 1 to the power of k plus 1 times 1 over k. So when k is 1, you just have negative 1 to the power of 2, which is just 1, times 1 over 1, which will give you 1. So that's how you get this one here. Okay, and so forth. So if you look at these two series, you realize that we've looked at series of these forms before. We've looked at 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 sixth, and so forth. And that's just summation from k from 0 to infinity of 1 half k, 1 half to the power of k, right? And that we know is the geometric series. So when you now alternate the signs, we call them alternating series. So in this case, this would be an alternating geometric series. Geometric series. So this would naturally be an alternating harmonic series. All right, in this section, we're going to talk about some tests for how and when an alternating series diverges or converges. So a series of these forms where the signs alternate are called alternating series. So we're going to begin with a theorem that we're not going to prove. This theorem is called the alternating series test. Right. Okay. Now the alternating series test says the alternating series summation of negative 1 to the power of k plus 1 ak converges provided the following is true. Provided ak is greater than or equal to ak plus 1 is greater than 0. So this just means that the sequence that forms a series is non-increasing. Or you can think of it as decreasing. All right. Secondly, the limit as k goes to 0 of ak is equal to 0. All right. So if you remember in the divergence test, we have that when limit as k goes to, k goes to infinity, not k goes to 0. The limit as k goes to infinity of ak, when it's not equal to 0, the series diverges. And when it's 0, it doesn't tell us anything. However, in this case, when this limit goes to 0, it actually helps us prove convergence. All right, convergence. Okay, let's do some examples. Okay, the first example, summation as k goes from 1 to infinity of the limit of the series -1 to the power of k plus 1 over 1 over k squared. Okay, let's look at this one. So this is our AK. So let's look at a few things. 1 over k, our AK, this is non-increasing. Because 1 over 1 is definitely greater than or equal to, or is definitely greater than 1 over 2, 1 over 3, and so forth. So it's non-increasing. Again, let's look at the limit. The limit as k goes to infinity of AK is the limit as k goes to infinity of 1 over k is 0. So by the alternating series test, we can conclude that sorry, this is AK. Why did I delete it? We can conclude that that our series, that the series converges. Alternating series test says our AKs have to be non-increasing, and the limit as k goes to infinity of AK has to be equal to 0. All right, let's try another one. Let's try this limit 2 minus 3 over 2 plus 4 over 3 minus 5 over 4. So let's write it as a series. So this is summation k from 0 to infinity, or let's do k from 1 to infinity. If we need to rewrite it, we rewrite it. So assuming we're adding 2 and 3 over 2 and 4 over 3 and so forth. So it's like you're adding 1 to the exponent, to the numerator and denominator. So let's look at this. I want to take you through the thought process of this. So you have 2, and then you have 2 plus 1 over 2, and then you have 3 plus 1 over 3, and then you have 5 or 4 plus 1 over 4. So that's what we have here. This is 2. This is 2 plus 1 over 2. This is 3 plus 1 over 3. This is 4 plus 1 over 4. All right? So, but now we have this minus here. And we have, let's forget about the signs first. Let's just assume that we're adding up all these numbers. So this number, this is like k plus 1. In general, it's k plus 1 over k. So let's write that first. Write it down first. This is k plus 1 over k. Now, we have to decide, now decide how to take care of the signs. When k is equal to 1, we get 2 over 1, which is just 2. But when k is equal to 1, we want to have the sign in front of 2 be positive. So we can write it as -1 to the power of 2, and that would be k plus 1. All right, so this would do it. So that will make sure we have a positive 1 here, and then we have a negative there, have a positive, then we have a negative, and so forth. Okay, so we have an AK. This is our AK. No, this is our AK. All right. Now, let's write AK down. AK is equal to k plus 1 over k. All right. So, which we can write as 1 plus 1 over k. This is decreasing. AK is decreasing. But now let's see, limit as k goes to infinity of 1 plus 1 over k. This limit is 1. So this limit is not equal to 0. Okay, so we can actually conclude something. What can we conclude? Can we conclude that the limit diverges? I'll tell you diverges. We'll come back and I'll tell you. The alternating series doesn't tell us directly. The alternating series test doesn't tell us that it diverges, but I can tell you diverges. All right. It tells us that when these two things happen, when it's decreasing and it's 0, then it diverges. It doesn't tell us that then it converges, sorry. It doesn't tell us that if the two of them don't hold, then it diverges. It's not if and only if. All right, so, but I claim it diverges. We'll talk about it in class. Okay, now, let's look at another one. I want you guys to actually look at this. K from 2 to infinity of -1 to the power of k, natural log of k over k. Okay, so I want you to show that it's decreasing. You can use derivatives to show that a derivative is always negative, and then show that the limit goes to 0, and then you're good. So this is our AK over here. My claim is that it converges. Does it converge? Use the alternating series test. We'll discuss it. Tell me I want you to try it and tell me your answer in class. So let's look at another theorem. Okay. So, definition. Okay. Consider the alternating series, -1 to the power of k, AK, right? Where AK, each AK is greater than 0. All right? Every AK is positive, right? If the summation, just this summation, AK, the absolute value of AK, let's make it absolute value, even though we've already determined that it's all positive. If the absolute value of AK, the summation of the absolute value of AK converges, we say that our original alternating series converges absolutely. So let's have a theorem. This theorem is the absolute convergence. Well, let's not give it a name. What? Forget about the name. Before I state the theorem, I wanna I want to say more things. Sorry. Okay. So if we have this alternating series, if this series right here converges, we say that our original series converges absolutely. Okay. If the original alternating series converges, but this the absolute value series diverges, we say that this series AK converges conditionally. All right. Now, I'm going to state a theorem. Two parts. The first part, if AK, this series converges, then this series must converge. All right. Why is my stuff not fitting in? Okay. All right. Converges. Now, number two, if the original alternating series, -1 to the power of k, AK, diverges, then the absolute value series diverges also. Okay, remember the terms: absolute convergence and absolute convergence and conditional convergence. So this theorem is just saying that absolute convergence implies convergence. Absolute convergence implies convergence. Okay. That's what the first part is saying. Now, let us do a few examples, at least one. Let's look at this series k from 1 to infinity of -1 to the power of k over the square root of k. Let's make it k plus 1. All right. So we can write this as in this form: summation k from 1 to infinity of -1 to the power of k plus 1, and then 1 over square root of k. So this is our AK, and so let's consider the summation k from 1 to infinity of 1 over square root of k. Let's see if this series converges absolutely. Okay. All right. So what I'm trying to do is I'm trying to figure out absolute convergence. So I'm asking the question, does it converge absolutely? Absolute convergence? Okay. So to do absolute convergence, we have to go with this. I'm going to enclose it in an absolute value. Enclose my AK in absolute value, even though it's already positive. So this will just give me what I have: k from 1 to infinity, 1 over square root of k. All right, and this is k from 1 to infinity of 1 over k to the power of 1/2. What kind of series is this? This is a P series with P less than 1. So it diverges. Thus, no absolute convergence. No absolute. It doesn't converge absolutely. All right. Conditional convergence. Let's look at conditional convergence, since there's no absolute convergence. So that means if we can just show that the original alternating series converges, then we obtain conditional convergence. So our original series, I'm going to copy and paste. Let's not get carried away writing a whole bunch of stuff. So we have that copy. I'm going to paste it over here. All right. So, oh, and I wrote it like this. Copy again. Paste it. Okay. So we have our AK. Is AK is 1 over square root of k. This is definitely decreasing. AK is decreasing. And limit as k goes to infinity of AK is equal to limit as k goes to infinity of 1 over the square root of k, and this is 0. So we can conclude by the alternating series test, our series converges. So the series, since this series converges, but it doesn't converge absolutely, we can now conclude that it's conditional convergence. All right. And I want you to try another one. I want you to try k from 1 to infinity of cosine of k over k squared. I want you to try this one. Okay. I'm gonna stop here.